Hello everybody, I'm Sayed Saeed Masumzadeh and I'm presenting the paper entitled The Self-Adaptive Performance Aware Capacity Controller in Overbooked Datacenters for IEEE International Conference on Cloud and Autonomic Computing 2016. Resource overbooking is a well-known technique which is used to mitigate the low resource utilization ratios by allocating more virtual machines than the physical resources. The advantage of resource overbooking is to increase the utilization in data center, but on the other hand, it increases the possibilities of having virtual machines interfering with each other. However, not all the VMs are equally affected by this interference. For instance, a deadline-constrained application, for example, a computationally intensive task, does not need to maintain an average performance all the time, as long as it completes the task in time. By contrast, an interactive application may require a certain minimum performance all the time. In order to treat VMs with different quality of service requirement, we use the KVM core pinning functionality to create different isolation level between virtual machines. We created two different groups, high quality of service application and low quality of service application. In the high quality of service application group, virtual CPUs are pinned to physical CPUs and get exclusive access to them. So no other virtual CPUs in other virtual machines can be pinned to these physical CPUs. In low quality of service application group, virtual CPUs are not pinned to any physical CPUs and can use any physical CPUs except the ones booked for high QS application. This quality of service classification, however, impacts the overall utilization when high quality of service VMs are over-provisioned. To deal with this problem, a conservative controller based on the high quality of service applications performance has been introduced in our previous work. This controller incrementally decreases their isolation level by sharing some of their cores. More specifically, at every control interval where a high quality of service VM is behaving better than needed, an extra physical core allocated to it will be shared with the low quality of service VMs. This process keeps on as long as the target performance of the high quality of service virtual machine is maintained. Otherwise, the maximum isolation level is established again to avoid any possible performance degradation by recovering the complete isolation. So, what is the problem of this conservative controller? Although this controller presents good results regarding performance isolation of the high quality of service applications, it works in a reactive manner. So it's very conservative. Therefore, it may have bigger impact in the overall utilization ratios than desired, especially with high fluctuating workloads. Furthermore, it may also affect the low QS applications due to abrupt reductions in the amount of cores that they are entitled to use, as high QS applications recover the isolation on all the cores at once. So what we proposed is a self-adaptive capacity controller exploiting an online machine learning approach to efficiently learn decision policies in terms of isolation level or the number of cores to share with regard to the application behavior. Our approach is based on a particular reinforcement learning technique called fuzzy Q learning, which is a combination of Q learning and fuzzy logic. Note that we will have an fuzzy Q learning agent inside each high QS virtual machine. But why we are using fuzzy system here? As Q learning is a table-driven learning algorithm, using fuzzy logic can facilitate it to deal with large or continuous state space, resulting in handling high dimensionality. In addition, using fuzzy logic can enable knowledge encapsulation into the learning table to merge a prior or expert knowledge into the problem. Let me go to the details of the algorithm and give you a definition from reinforcement learning. Reinforcement learning comprises a set of machine learning methods designed to address a particular learning task in which an agent is placed in an unknown environment and is allowed to make decisions or take actions which can change its state in the environment and bring it delayed numerical rewards. The goal of the agent is to learn a policy that tells it what action or decisions to take or make in order to maximize the cumulative reward over time. So, Q-learning is a popular reinforcement learning algorithm. It represents the learning knowledge by means of a Q table, whose Q values are defined for each state action pair or state decision pair, determining the expected cumulative reward that can be received by taking that action or making that decision in that state and following an optimal policy after that. So an optimal policy can be constructed by simply selecting the action or decision with highest value in the Q table for each state. The reinforcement learning problem is modeled as follows. The state vector X is composed of values of representative variables capturing the surrounding environment. S is the set of possible states that the agent can perceive from the environment. The set of action A represent the decisions that the agent can make based on the state vector X. So the X actually is a state vector and the A is the set of actions. Based on X and the corresponding Q value, the most suitable action which is belong to the set of A is selected and executed. After the execution of action in X, which is the state, the agent receive an immediate scalar reward R, and the corresponding Q value is updated by the TD learning or temporal difference learning, which according actually to this rule. So we can update actually the Q table by TD learning and then construct the policy to map the state to decision based on that. So the most significant drawback of Q learning is that it cannot be used in case that the state space is large, a situation found in many real-world problems. Since it uses mainly large memory for saving Q table, and the Q table actually using for keeping the track of the state action quality values. Apart from it, even if the system provides such large memory for keeping actually Q table, the learning agents needs lots of trials and episodes to learn desired behavior, resulting in increasing the cost of learning. So fuzzy Q learning is a fuzzy extension of the Q learning algorithm being able to overcome this problem. It allows us to encapsulate expert knowledge also into the learning table, which results in speeding up the learning process. In fuzzy Q learning, the decision-making part is represented by a fuzzy inference system that consider continuous large discrete states as input. The idea of the fuzzy Q learning algorithm is to use a compact version of the Q table to represent learning knowledge. So now let me explain how we modeled our problem into the FQL. FQL, or generally Q learning, or more generally reinforcement learning algorithm, has three main components: state, action, and reward function, as we explained in previous slides. The combination of the current response time and the current isolation level in terms of number of shared cores describe each state inside a high quality of service virtual machine. So these two characteristics, response time and the current isolation level, have enough information to represent a predictable application behavior. So you can see the state X is a combination of response time and number of shared cores. Each element of the action set A denotes the number of cores needed in isolation for transiting from current state to the next state. So the action and the state are clear now. Let me explain the reward function. The design of reward function is a key to build reinforcement learning system. It maps each perceived state action pair of the environment to a single number indicating the intrinsic desirability of the state action. The goal of the reinforcement learning is to maximize the cumulative reward over time. In our system, the reinforcement learning tries to optimize the trade-off between sharing capacity and the performance over time. So the reward function can return a value determining success rate, here maximizing the number of shared cores and minimizing the response time. So as you see in the equation for reward function, NC is number of cores is the number of cores in isolation, and TC is the total number of physical cores assigned to a high QSV. RT is the response time of the application on that moment, and TR is the target response time. So it's obvious that if the high QSVM controller shared its cores as much as possible while keeping the response time as far below as possible from the target response time, it will receive more reward. If the reward is close to zero, this implies that the action is not effective and a negative reward is considered as punishment for the learning agent. Now the experiments. The tests are conducted on two machines, one hosting application and one generating the workload, connected through a 1 GB link. The first machine is a server consisting of a total of 32 cores and 56 GB of memory. KVM was used as a hypervisor and each application was deployed inside a VM. The second machine is a 4-core desktop with 16 GB of memory. As regards to the workload, a number of queries have been generated using information extracted from different days of the Wikipedia traces. The first VM classes is represented by line living VMs running interactive applications that usually present some seasonality pattern in their use. For this application class, the high QS applications, we have used the robust and robust cloud benchmarks, which are an Action website benchmark modeled after eBay and /dot respectively. The second VM class consists of different type of relatively short living, non-interactive VMs. To increase the uncertainty in the system and thus creating a more realistic aggregated workload, we created different virtual machines that run shell scripts that consume random amount of CPU and memory over time. This creates a set of VMs with highly heterogeneous and time-varying resource requirements, with both bursty and steady behavior in their resource consumption. On the other hand, to have a measurable performance of this class of VMs, we have also created different types of VMs that continuously solve random Sudoku and report their corresponding throughput achieved over time. We compared proposed fuzzy Q-learning capacity controller, let's call it FQL capacity controller, with the previous conservative capacity controller, and let's call it CC6. So we want actually to compare proposed FQL capacity controller with CC6 capacity controller. We measure the average and we measured the average and 95 percentile response time for the robust and robust virtual machines in order to ensure that high quality of service application performance is maintained. On the other hand, we evaluate the overall utilization and number of shared cores over time, as well as the number of Sudoku VMs concurrently running. The throughput achieved by the Sudoku VMs is also measured to ensure that low quality of service application performance is acceptable. This figure shows the performance comparison between CC6 and FQL as regards to the robust application performance. As the left two figures shows, there is no remarkable difference at the response time, since the robust VM present a linear performance regarding the number of requests, which facilitates to keep the response time within the desired limits. However, it is highlighted that the trend for FQL is slightly flatter due to sharing a more stable number of cores over time. It can be seen at the right figure that the amount of core shared over time is pretty similar for both approaches. However, FQL shares slightly more cores, it's obvious. Both of them sharing all the cores around half of the time. However, as highlighted in the left two figures, the number of cores shared over time quickly and largely fluctuates for CC6, while remains more stable for our approach, FQL approach. This figure actually shows the same comparison between CC6 and FQL, but for the robust application, which presents less linear behavior with respect to the number of requests per second. In this case, as the performance fluctuates more, we show its evaluation over 3 days. The first column is for first day and the second column is for the second day, and the last column shows the result for the third day. These results in 3 days can highlight the learning process of the FQL approach. Although the performance is reasonably good for the first day, in the first column, as you can see in the first column, for both approaches, with a slight improvement for the FQL, the performance is improved day by day for the FQL approach. In the second day, as you see in the second column, the differences between CC6 and FQL are noticeable, with an overall reduction of the response time. Not only the overall response time is reduced, but also the fluctuations, both in number and size. These differences are even more remarkable at third day, in third column, where thanks to the learning, the FQL approach remarkably reduces the response time, as well as presents a more constant behavior compared to CC6. Additionally, as depicted in this figure, the FQL approach is also able to share more cores over time. The left figure shows the aggregated number of cores shared by BOS FQL agents inside BOS high quality of service VMs. The box plot clearly highlights the smaller variation in the overall number of cores shared over time, as well as the higher average. Additionally, the evolution over time is depicted at the right figure, where the smaller fluctuations over time are also clearly highlighted. So as the previous slides showed, the FQL-based capacity controller presents a more efficient sharing mechanism where more cores are shared, and in turn more VMs can be accepted. This is highlighted in these figures, where a histogram for the amount of pseudocode VMs concurrently running is depicted. Only the first bar are larger for CC6, which means there are fewer concurrently running pseudocode VMs during longer period of time. By contrast, all the bars for the higher amount of concurrently running pseudocode VMs from 7 onwards are larger for FQL, which means that most of the time there are more pseudocode VMs concurrently running when using FQL. In addition, a summary box plot is presented in the right figure, highlighting a 5% improvement in the number of concurrently running VMs within an already overbooked system. And finally, thanks to FQL capacity controller, the overall utilization also rises as shown in this figure, where the average utilization along the 3 days experiments is depicted. And the conclusion, we presented a fuzzy Q-learning based capacity controller that dynamically decides how much capacity each high quality of service VM can share with low quality of service VMs, or in the other words, how much the isolation level between them is reduced. We used an enhancement strategy to mix between reactive and proactive actions to have more stable performance, which I didn't explain in the slides because of having limitation in time, and you can find more information and also more results in the paper. As a result, more low quality of service VMs can be processed without affecting the high quality of service VM's performance, consequently making a more efficient use of the available resources and increasing the overall utilization. Thanks for your attention.